Hello community! Today we talk about Monte Carlo empowered AI agent, and the topic is simple. We just ask, hey, what if artificial intelligence could explore all possible futures before AI makes a decision? And you might say, hey, that sounds uncalculable. Well, Monte Carlo techniques that we know from theoretical physics, from mathematics, make this futuristic vision a reality. And today we will implement this and we will try to understand what's happening in AI after each step. So here we have the simplest idea. We have here a square and we have a quadrant of a circle. And as you can see, this is Monte Carlo in the lowest dimension possible. We just throw dots, and given the amount of dots, and we have about 9,500, 9,000, 10,000 dots, we can calculate pi without knowing anything about pi. Just throwing dots at a two-dimensional manifold, we can calculate hidden features of geometric shapes in n-dimensional spaces. And this is exactly what we are going to use now. Because imagine, in the simplest case, each dimension integrates now a new possible action in our future. And you know what? AI has the compute power to go not just to two dimensions, but to hundreds of dimensions or thousands of dimensions and calculate the probabilities. You remember in my last video I was talking here about 3 beautiful new research papers here at the end of August 2024. And last time here we had a look here at Stanford University, MIT and Boston University. And I showed you here the new core of AI agent and what they do, how they create now new AI agents that can do academic reviews like a human reviewer. So AI does not only do now the experiments of humans, but now AI now evaluates the work of humans. Beautiful. But today we're gonna look here at the very first row. Because as you can see, the PDF number 1 and PDF number 3, here we have both Monte Carlo simulation. And we look at Monte Carlo skill estimation using here a particle filtering in a dynamic Bayesian network. And you might say, that sounds interesting. Yes, absolutely. Because we have an objective. Because we want here in the first case to estimate the agent skills. And we go here for one skill set, and this is the execution skill set. So how good is this AI in deciding something, in executing new ideas? So the task is simple. We just have, or the AI just has to choose the right future with the highest probability of success for a particular task. And the AI just has to go in a 1000 dimensional probability space and just calculate the right path to the future that I provide in my task. Find the solution, find the path forward. And then after we have solved this simple case, we will look here at a system of multi-agents where we now challenge the AI to develop here strategic skills for gameplay like Go or AlphaGo, maybe. And we will use here Monte Carlo Tree Search that we combine with some new technologies. So for my green grasshopper, it is easy. We just have a look now, hey, what decisions can this AI agent think of? How complex can those decisions be? How good does an AI agent decide? Given its specific training, given its specific memory that it already executed and has already some evaluation results of its decision. This is now the topic we're gonna have a look. So let us start here with the first idea, Bayes network. Now, Thomas Bayes, born in 1701, and more than 300 years ago, we have here this probabilistic, let's say, formula in statistics, where we can calculate here the posterior probability, the probability of the hypothesis H being true given the evidence, the facts that we see, the evidence E. And then we have here the likelihood, which is simply the probability of observing the evidence given that the hypothesis H is true, we have the prior probability. This is the initial probability of the hypothesis H before observing now the evidence, the fact E. And then we have the marginal likelihood, or the evidence as we call it, the total probability of the evidence under all possible hypotheses. So 300-year-old idea of probabilistic. Isn't this beautiful for my green grasshoppers? Now we move now from Bayes' theorem to Bayes' network. And a Bayesian network is simply also known as a belief network you can find in the literature. This is simply a graphical idea, a graphical model that represents a set of variables. Maybe some are hidden, maybe only some are known, and their conditional dependencies through a DAG, a directed acyclic graph. Bayesian network provide now a way to model the joint probability distribution, and this is the most important part here, the joint probability distribution, as a set of random variables by breaking down a complex relationship into simpler conditional dependencies. And you notice, whenever, even in prompt engineering, we have a real complex prompt, either we as humans or some prompt optimizer breaks down a complex task description into multiple step-by-step mini-tasks. We do this here now also in statistics. Now, the components of a Bayesian network are simple. We have the nodes. Each node in a graph represents a random variable, and they can either be observable data or latent variables like hidden states. And then we have edges. And these edges are simply, imagine like arrows pointing from one node to the next one, and they represent here our conditional dependencies. And if there's an edge from node A to the node B, it simply indicates that B is conditionally dependent on A. And then comes now the beauty where we have our conditional probability distribution. This is now the beauty that we can use here, Bayes' theorem on Bayes networks. So each node in the network is associated with a conditional probability distribution that quantifies the relationship between the node and its parents. So this defines now the probability of each possible state of the node given the state of its parent nodes. So this is how we can build, how we can simulate future steps in a graph network. And now, of course, the real beauty is that we have here a factorization that is working here in Bayes' network. So we have our DAG, and then we have the factorization of the joint probability. And without this, let's call it a trick, no, let's call it an idea implementation, we would have real problems to calculate here the joint probability. But with this factorization taking place, this is what makes here a Bayesian network computational efficient for representing and reasoning about future, whatever happens in the future, about complex distribution of dependencies of our parameter of our system in a future development, how the future will roll out if we have new parameters, if we have new dimension in our action space, if we have new dimension in our decision complexity. So you understand, hey, yeah, this factorization, this makes life easier to calculate this. Talking about making life easier, let's make it a little bit more complicated. Going here from a normal stationary Bayesian network to a dynamic Bayesian network. So now we understand, if we go now with a dynamic version, this dynamic version provides you the underlying probabilistic model that we need that represents how the agent's skill will evolve over time. Let's say the agent is learning, the agent has some experience, the agent makes some wrong decision, notices that this is the wrong one, goes back on the decisions and choose another decision. It chooses another path into the future. So you see, this now defines here the relationship between the variables. These are now the agent's skills at different times and the observation of the agent performance. And how these variables depend on each other across different time steps. So complexity is a little bit increased since we operate now with different time slices. But in theory, we still use here Bayes' theorem. Now, talking about here time slices and temporal dependencies, we are now working here with a temporal dynamical structure because we want now understand here the skill at the previous time and how the observation, how the action outcomes of our AI agent, how they depend now on current skills. So this means this structure allows the system to incorporate past information to predict future states. But careful, you have to get all the variables right. And you have to build a system that is really able to have here a multi-dependencies intertemporal dynamics of your system. Okay, great. Now we have this. Now, reading now the literature on this topic, and believe me, even Bayes' theory is 300 years old, so you can imagine this is really a topic of research. Unfortunately, this dynamic Bayesian network alone is not enough for us to calculate here, for our AI agent to calculate here the skill estimation in future learning paths. Why? Because we do have now a high complexity given the time slots that we have to compute, plus the dimensions of the action space and the decision spaces. Plus, we have a nonlinearity. So we cannot work here with Kalman filter or whatever you know here from the simplest cases. So the relationship between the variables here in this dynamic Bayesian network can be highly complex and nonlinear. And therefore, we cannot solve it analytically. So we have constructed here this structure. We know now the dependencies. We have here a beautiful, completely operational system. But we can't run it. We can't compute it because it is too complex for our numerical analytical computations. So this dynamic Bayesian network defines here a probabilistic model, but to make predictions now on the future, which path to choose, how to go on, or estimating the current skill level based on the observed actions, so that we say, hey, this is a real advanced AI agent, and his particular skill, let's say, to make decision, is really 8 out of 10, we need now to perform inference. You know this from classical statistics. And inference in this here dynamic Bayesian networks, especially when the model is complex and the state space is large. Yes, we also have an action space, we have a decision space, and we have now the state space of the system at a particular time. To calculate this can be computationally challenging. So this means, simple words, analytical solution of our beautiful structure are often impossible. So you might say, what? We built this probability structure and now we fail because we cannot compute it? You remember that I told you there's the Monte Carlo methodology. And look, we do this here in just 2 dimensions. We have X and we have Y. And now we have multiple spaces with high dimensions. And you just imagine now we take this 2-dimensional idea to discover the hidden parameter pi. We take it now to a 1000-dimensional state space and we calculate here with our simple dots here and to find the hidden parameters, our skill levels, if we just look at the action of the AI agent in a particular step, in a particular time step. Now, there are different Monte Carlo methodologies that maybe you know from mathematics or theoretical physics, or maybe even from finance. I've seen they calculated also with Monte Carlo. But we go here with particle filtering. And maybe you know it as a sequential Monte Carlo methodology. This is simply a set of algorithms used to estimate the state of a dynamic system when this system is only partially observed and definitely nonlinear and highly complex. So these methods now allow us to calculate here, and they are particularly useful here for estimating the posterior distribution of a system state when the model and the measurements are both non-linear and the distribution is non-Gaussian. And you say, how is it possible that we can compute something with this complexity? Well, this is the beauty, if you want, of Monte Carlo methodologies. Now, the particle filter algorithm is, just think about, this is the algorithm you have to run. So at first you have an initialization here with a set of n particles. Remember the little dots that we throw here on our little quadrant here of the circle where we have this decision that we want to calculate pi. Beautiful. Then we have the prediction, if you want the time update. So for each particle I, for each dot that we throw now at this two-dimensional, but we do it, of course, in a higher dimensional space, for each particle I predict the next state using here the state transition model. This step generates a set of predicted particles based on the previous state and the process noise. Then we do the update for each particle, compute here a weight based on the likelihood of the observed measurement. Then we normalize it, and then we do a resampling of the particle based on their normalized weights to focus on the most likely states. Beautiful. So you just follow this recipe of the particle filter algorithm, and then we achieved it more or less. Because now we have a methodology to explore here the complete space of all possible states of our nonlinear, highly complex system, the structure here of our interaction and the future interaction that could define here the best possible outcome. Great. Monte Carlo methods particle filtering used to perform inference in situations where exact analytical solutions are not feasible, maybe not possible. So we approximate now. We have not a clear mathematical analytical solution, but we have to approximate now the probability distribution of the hidden state. In our case, it is the skill level of our AI agent by using a set of particles. We just sample here the event. So these particles represent possible values of the skill levels, and the distribution of particles approximated to posterior distribution. And this is a methodology we use when we deal with nonlinear models and non-Gaussian distribution in complex real-world scenarios, and this is exactly where we are. Particle filters can handle the complexity of a dynamic Bayesian network by using random sampling to explore the space of possible states. So we do what I showed you here with this simple two-dimensional Monte Carlo simulation to calculate pi. Now, in, let's say, a 1000-dimensional vector space, maybe tensor space, where we do exactly the same idea, but just the computational complexity is a little bit higher. Therefore, we need Monte Carlo. But there's no theoretical problem in doing this, and I hope that I've shown you now a little bit of the methodology that we use. If you want here another kind of introduction, I would like to recommend you two papers. And this paper here is called an empirical Bayes approximation for estimating the skill models for professional dart players. And hey, here we are, a professional dart here. This is just a two-dimensional problem, no? We just have an X and a Y elongation here of the dart, so where our dots could fly. So very nice, mid of April 2024. Or if you wanted a little bit more, let's say, advanced, where we go here with sequential Monte Carlos and discrete hidden Markov models, I would recommend this also from mid of April 2024. Normal Computing, School of Mathematics, University of Bristol, and Department of Mathematics and Statistics, Lancaster University, and the University of Torino. A state space perspective on modeling and inference on skill ratings. So this is the more advanced paper. Maybe you read this here in the second position, but this gives you also a very nice introduction to this topic here of sequential Monte Carlos with discrete hidden Markov models. So we use here the skill estimation of the Monte Carlo simulation. This operates now within a Bayesian network, representing here the agent skill levels, the target actions, and the executed actions as random variables. And now a probability distribution over the space of possible skill levels will be updated each time an executed action is observed, that we have an event, that we have new data. And what differentiates now this new methodology from the old work is that the fact that the skill levels are represented as time-varying random variables in the dynamic Bayesian network, and that a particle filter is then used as an inference method to reason about the involved random variables. And you might say, but wait a second, Thomas Bayes' framework was a probabilistic framework. And Monte Carlo here is also a probabilistic framework. So we have now two probabilistic frameworks that we need to solve here our problem, because we have one Monte Carlo and we have one Bayesian network. Yes, exactly. And there's the beauty. Now, if you want to have a little bit a deep dive, here are the random variables again, but with a little bit more characteristic, where I show you what is observed, what is unobserved, what is in the inference happening. So, of course, we have the execution skill and the decision-making skill. And remember that last time I showed you here this paper submitted here in August 2023 and published here in May 2024 in the Journal of Artificial Intelligence Research. And here our two authors from the current publication here, they give you here estimating here the agent skill in a continuous action domain. And they talk exactly about here the ability to select effective actions. This means the decision-making skills and how precisely it can execute those selected actions. And this means the execution skills. And here we have it again. Here are decision-making skills, now in the advanced version a year later, and the execution skills. But of course, we need also here data. No? We need here the executed actions and the target actions. And here you have the characteristics still unobserved. The executed actions, so the events, if you want, they are now observed. They are directly observed, and we see the action that the agent actually execute, and therefore we can have then a further analyzation of all those hidden, these unseen parameters of our system. So if you want a little bit more of a deep dive, this is for you. Beautiful. So we have now multiple agents are used here in this particular experiment to explore here a diverse range of decision-making strategies. And you see, we are moving slowly here from our first PDF into the third PDF, but slowly. We are still here at PDF number 1. But it is clear. Now, we have multiple decision-making strategies. Also, one agent has multiple strategies it can follow. And each strategy has a unique approach in selecting the next actions. Because what is a strategy different if then you have simply a list of possible actions that you would like to perform, to execute. So by varying now both the decision-making strategies and this is what we are looking for, the skill level, and here to be precise here, the execution skill levels of our AI agents. Now, those two beautiful researchers that I just showed you in the publication, they can now investigate how those factors interact and influence the overall performance of the agent. So, beautiful. We have now exactly what they were analyzing. And remember, we have just two, the decision-making strategy and the execution skill levels. And we are just looking at those simple dependencies. And there's a set of other dependencies that we have to solve in the next video. So those different agents. So we now focus here on one particular skill level. Those different agents in the experiment represent various decision-making strategies, each with its own unique way of selecting specific actions. And by using now multiple agents, where each agent is doing something a little bit different than the other one, the researchers can then explore how different decision-making processes impact the overall performance and how they interact with the agent execution skill levels. So what we do now is we don't say, okay, we have just one agent with a complexity, but we break it down into multiple simpler agents. Let's have a look at this. At first, of course, we have the rational agent. selects the optimal action that maximizes the expected reward given the agent's execution skill level. So this agent represents the ideal decision-making process where the agent makes the best possible decision based on the currently available information in your time slot. So it serves here as a baseline or as a control group to compare how much more complex or less rational decision-making processes will perform against this particular benchmark. So what is the simplest agent you can think of? It's just a flip agent, no? Now, the behavior of this flip agent is simply, sometimes it selects a random action. So this introduces here some randomness and exploration in the decision-making process. And we have the equilibrium between exploration and exploitation here. So we go here a little bit crazy and we go random. What else we have? Let's say we have a softmax agent. Now, behavior is to select actions probabilistically with the probability of each action being related to expected rewards. And this behavior is governed by a parameter lambda, which controls here the degree of the randomness. And to study here the decision-making strategy where the agent doesn't always pick the highest reward action, but instead samples from a distribution over possible actions. And this helps us to understand how a more nuanced decision-making process performs. We can have an agent that is a rebellion, says, hey, never mind, I choose an action that is the farthest from the optimal one. But still achieving here a certain level of reward, otherwise we would just jump out of our system. And the purpose is simple, to explore how agents that do not necessarily seek the highest reward, but rather choose some suboptimal actions. Maybe you want have here deception, a strategic reason that you want to show your opponent, hey, now I take this particular action, but this is just here that you want to, let's say, irritate your partner a little bit. So this could now simulate scenarios where an agent might want to mislead others in a competitive setting, and we have a game theory setting coming up, so you see exactly where we're going with those. So there you have it. A simple flip agent, a simple softmax agent, and then an agent that says, hey, I go with suboptimal structures. And now we are there, because now we understand how those multiple agents perform. We see the events, we see their actions, and now we can compare them. And now we can say, okay, here the softmax agent delivers here a good result, or here this random action is really necessary to jump out of a local minimum, for example. So using now these multiple agents allow the study for different decision-making strategies to be explored, plus their interaction with varying execution skills. So here we go. Comparison of strategies. By having agents with different decision-making processes, softmax or just going crazy, the researcher can compare which strategies are more effective under various conditions. Plus, the experiments can reveal how the execution skills and the decision-making processes interact. For example, how does a rational agent with a high execution skill perform if you compare it to a softmax agent with the same execution skill? So what is now better performing? If we do the generalization, so using multiple type of agents increases here the generalizability of the findings, showing that the conclusions hold across different types of decision-making processes and are not specific to a single type of agents. So by testing here with different combination of skill distributions, and we do not go here with only symmetric, but we also purposeful go and choose asymmetric, the experiments can identify which strategies are robust under various conditions. So a lot of work to explore to understand which agent with particular execution skills and different decision-making strategies, which agent performs best. So now that we have it, now we have a single AI agent operating here in a simple environment. And now with this tool set that we have now, we take now the step here to develop now in a multi-agent environment. Let's say it is a competitive games environment. Now we want that the system understands that it has to develop, to self-reflect, to self-enhance, to self-learn new strategic skills as an AI agent to solve here or to win here this competitive game. Therefore, we will use another Monte Carlo simulation, but now simpler. Don't worry, it will be real simple. We just do a Monte Carlo tree search mechanism that we combine with some other strategies. So then as it's called in the PDF, we have now an AI strategist that now does not only have here an execution performance or has a particular skill level at doing here the planning, but now we have, if you want here, an AI agent that has here improved strategic skills in multi-agent environments. So we have now an agent that is a little bit more clever than all the rest of the agents. And now it becomes interesting because this single agent now, this is now really important. The performance of this strategic agent will determine the future, will determine the steps all the other little minion agents take on the path forward to find here the perfect solution in the future, to find the shortest path, to find here the shortest solution with minimum resources or whatever you have as a problem. This strategic AI agent will change the game. And yeah, absolutely. This is the publication if you want to already read it. We will encounter some beautiful complexity, and finally we will able now coordinating now our knowledge how to do this in Monte Carlo and why we have to do Monte Carlo. We will finally be able to do here the coding, and we have here a complete GitHub repo where everything is already coded for us, so we can jump in and do some experiments, whatever you are interested in. For example, here are Python files for the Monte Carlo Tree Search algorithms. But more about this in my next video.